NASA says its Voyager 1 probe, the most distant man-made object in the universe, is once again sending usable information back to Earth. Launched in 1977, Voyager 1 has made headlines for more than 45 years by revealing some of the most shocking and unexpected secrets of interstellar space. Not only did NASA use the spacecraft to discover the massive storm on Jupiter and the rings around Saturn shortly after its official launch, but more recently, NASA has alerted the world to a strange and seemingly impossible discovery from Voyager 1 that has left scientists both confused and worried. Scientists are confused because the information coming from the system that controls Voyager 1's operations does not, in any way, match the spacecraft's recent activities. What could this impossible discovery be, and what is the way forward? Join us on a journey into space to discover what is happening in our universe. The unexpected signals from Voyager 1 have emerged as the spacecraft has been traveling through space for 47 years since its launch, still exploring regions beyond our solar system known as interstellar space. Recently, however, it has developed a problem that has puzzled the team of scientists and engineers monitoring it from Earth. Despite its age and its distance of 15 billion miles from our planet, Voyager 1 continues to function well. It can receive and carry out commands from NASA and collect and transmit scientific data back to Earth. But there's a particular problem with one of its key systems that's serious enough to cause concern. This system, called the Attitude Articulation and Control System, AACS, controls the spacecraft's orientation in space and ensures that its high-gain antenna remains pointed at the Earth to send data back to NASA. However, the data readings from this system are not consistent with its recent activities. What Voyager 1 is actually doing remains uncertain because, while it appears to be operating correctly, the information sent back by the AACS appears to be random or even impossible. One of the challenges in dealing with this problem is the vast distance between Voyager 1 and Earth. Because Voyager 1 is in interstellar space, a signal or light takes 20 hours and 33 minutes to travel one way, meaning that it takes over 41 hours to send a message to Voyager and receive a response. Despite this delay, the team has determined that the AACS is probably still functioning, as the unusual data readings from the system have not yet triggered a safe mode. In safe mode, only essential operations are performed, allowing engineers to diagnose and fix problems that could threaten the spacecraft. Interestingly, the signal from Voyager 1 remains as strong as ever, suggesting that its antenna is still pointing accurately at Earth. The team of scientists and engineers is currently investigating whether the AACS itself is generating faulty data or whether another system is causing the problem. They are trying to understand why the data from this instrument does not match the actual operation of Voyager. The Voyager 1 investigation team is working to uncover the nature of this puzzling problem, as they cannot yet determine whether it will affect the spacecraft's ability to collect and transmit scientific data. This uncertainty stems from a NASA publication in 2022. Suzanne Dodd, project manager for both Voyager 1 and 2 at NASA's Jet Propulsion Laboratory in Pasadena, California, noted that this type of mystery is expected at this stage of the Voyager mission. Dodd explained that Voyager 1 is nearly 45 years old, far beyond the original expectations of the mission planners, and is now traversing interstellar space, an area of high radiation where no other spacecraft has ventured, presenting significant challenges to the engineering team. Despite these challenges, Dodd is confident that if there is a solution to the AACS problem, her team will find it. If they cannot identify the cause, they may have to adapt, possibly by modifying software or using a backup hardware system. If the source of the problem is found, Voyager has sustained operations by utilizing backup systems over the years. For instance, in 2017, it successfully used thrusters first activated during its planetary encounters in the 1970s. These thrusters had been inactive for 37 years but still functioned when needed. Given the probe's age and limited power generation, many subsystems and heaters have been shut down over time to conserve power for critical systems and scientific instruments. As Voyager 1 faces this question today, it recalls one of its most historic moments: its arrival at Jupiter in 1979. Voyager 1 made many important discoveries that changed our understanding of the giant planet Jupiter. For example, Voyager 1 discovered that Jupiter has a ring system. Previously, scientists thought only Saturn had rings. Jupiter's rings are faint and mostly made up of tiny particles of dust, making them difficult to see from Earth. but Voyager 1's close-up images showed them clearly. Voyager 1 also studied Jupiter's Great Red Spot, a massive storm larger than Earth that has been raging for at least 400 years. Detailed images of the red spot helped scientists learn more about its structure and behavior, showing strong winds moving in opposite directions around its center and revealing it to be a complex weather system. In addition to Jupiter's rings and the Great Red Spot, Voyager 1 revealed several other fascinating aspects of Jupiter, including clouds, smaller storms, lightning, and auroras similar to those on Earth. These images helped scientists better understand Jupiter's atmosphere and its similarities and differences to Earth's weather systems. After exploring Jupiter, Voyager 1 continued through the solar system, reaching Saturn in 1980, where it made equally fascinating discoveries about Saturn, its moons, and its massive ring system. One notable discovery was the identification of new moons around Saturn, adding to the known list of its natural satellites. These moons varied in size and composition, adding to the knowledge of Saturn's moon system. Voyager 1's detailed study of Saturn's rings revealed that they are made up of countless particles, ranging in size from tiny grains to large boulders, orbiting Saturn in an intricate ring system. The spacecraft's observations showed that Saturn's rings aren't solid, but are made up of many rings, gaps, and divisions formed by gravitational interactions with Saturn's moons, creating complex and constantly changing patterns. Voyager 1 also captured stunning images of Saturn's moons, including the largest, Titan, providing insights into the geology and surface features of these moons, helping scientists to understand their origin and evolution. As well as observing the physical characteristics of Jupiter and Saturn, Voyager 1 took a closer look at two of the largest moons, Europa and Enceladus, and found evidence that both may have hidden oceans beneath their icy surfaces. Europa, one of Jupiter's largest moons, has intrigued scientists for some time because of evidence of a subsurface ocean beneath its frozen crust. Features such as cracks and ridges suggest that gravitational forces from Jupiter and nearby moons could be causing tectonic activity beneath Europa's ice. The possibility of an ocean excites scientists because where there's liquid water, there could be life. If Europa's ocean contains hydrothermal vents similar to those on Earth, it could create conditions suitable for tiny life forms. Enceladus, one of Saturn's moons, also has a hidden ocean beneath its icy surface. During its mission around Saturn, the Cassini spacecraft detected jets of water vapor emanating from Enceladus, suggesting that water beneath the surface occasionally erupts into space. These water jets contained organic molecules, or the building blocks of life, and Cassini found evidence of hydrothermal activity on Enceladus's ocean floor, further suggesting that there may be a dynamic environment beneath the ice. These discoveries on Europa and Enceladus have led scientists to consider the possibility of life beyond Earth, and NASA has plans for missions such as Europa Clipper to explore Europa, as well as future missions to study Enceladus in more detail. Voyager 1's discoveries didn't stop at the moons of Jupiter and Saturn. NASA has uncovered even more fascinating information about these planets. Meanwhile, Voyager 2, the twin spacecraft of Voyager 1, is also operating in interstellar space, currently 12.1 billion miles, 19.5 billion kilometers, from Earth, further than Neptune, the furthest planet from Earth. Both Voyager 1 and Voyager 2, launched in 1977, have gone beyond their original missions and are now collecting data from interstellar space that is helping scientists understand the heliosphere, the bubble created by the Sun that extends beyond the planets in our solar system. In 2018, Voyager 2 made a landmark discovery when it became the second man-made object to enter interstellar space, providing insights into the Sun's bubble-like boundary. On the 5th of November, data from Voyager 2 revealed that it had crossed the heliopause, the boundary where the Sun's hot solar wind meets the cold plasma of interstellar space. The crossing showed a decrease in solar wind particles, confirming its entry into interstellar space over 11 billion miles from the Sun, and a solid interstellar magnetic field stronger than that detected by Voyager 1. Scientists continue studying data from Voyager 2 to understand the Sun's interactions with interstellar space, as shock waves from the Sun can pass through the heliopause into the interstellar medium, similar to how shock waves from supernovas move through space. Early data from Voyager 2's crossing is building a detailed picture of what happens in the space between the Sun and the interstellar medium, offering insights relevant to other star systems. By comparing Voyager 2's findings with those of Voyager 1, scientists gain valuable perspectives and are hopeful for another interstellar probe to gather even more data. Voyager 2, similar to Voyager 1, has made significant discoveries, including observing moons around Jupiter. In 1979, it spotted a small moon called Adrastea, marking the first time a moon was found using images from a spacecraft in space rather than a telescope on Earth. Adrastea, named after a figure in Greek mythology, is unique as it completes an orbit around Jupiter in less time than the planet's rotation. It lies on the edge of Jupiter's main ring and is believed to be a key source of the dust that composes the ring. Although the Galileo spacecraft observed it in the 1990s, we still know little about its composition and appearance beyond its size and that it always faces Jupiter. Adrastea was discovered by scientists David Jewett and Edward Danielson, who found it as a tiny dot in photos taken by Voyager 2 on July 8, 1979, and the moon received its name in 1983. The Juno spacecraft, which reached Jupiter in 2016, might eventually capture some images of Adrastea, although its primary mission is to study Jupiter itself. Adrastea, the smallest and second closest of Jupiter's inner moons, orbits the planet at a distance of about 129,000 kilometers, approximately 1.86 times Jupiter's diameter. It has an almost circular orbit and stays close to Jupiter's equatorial plane. Its orbit is smaller than Jupiter's synchronous orbit radius, meaning it is gradually moving closer to Jupiter and may one day crash into it. If Adrastea is as dense as another moon, Amalthea, its orbit, would actually be too close to Jupiter to remain intact. However, its current distance from the planet has allowed it to stay in orbit. The Voyager probes, initially expected to last only 5 years, have been operating for 42 years, defying expectations thanks to engineers dedicated to keeping them functional. Engineers have devised new plans to extend Voyager 1 and 2's missions, enabling scientists to continue receiving critical data from an unexplored region of space. The main challenge in keeping these spacecraft operational is maintaining enough power for their scientific instruments and heaters. Both are over 11 billion miles from the Sun, where temperatures are extremely low, so the heaters are crucial for their survival. The spacecraft's power systems have decreased in efficiency, producing about 40% less power than they did at launch. The probe's thrusters, which release small bursts to maintain orientation and communication with Earth, are also aging. Voyager 2, for example, recently activated thrusters last used during its Neptune flyby,